This video is sponsored by Google Security.
As is now tradition, this video is also available as an article on my blog. If you're a patron, 10 euros per month or above, you can go read it right now. If not, you can just keep watching the video for free and get access to the article 6 months from now. So you can go code listings, you can copy paste the things, you can go at your own pace and everything. Today we're going to talk about the case for sends io. The most popular option to decompress zip files from the Rust programming language is a crate simply named zip. At the time of this recording, it has 48 million downloads. It's fully featured, supporting various compression methods, encryption, and even supports writing zip files. However, that is not the crate that everyone uses to read zip files. Some applications benefit from using asynchronous I/O, especially if they decompress archives that they download from the network. Such is the case, for example, of the UV Python package manager written in Rust. UV doesn't use the zip crate, it uses the async zip crate, which is maintained by a single person and gets a lot less attention. This situation is fairly common in Rust. The same code gets written against synchronous interfaces and async interfaces. This results in a split ecosystem, duplication of effort, and of course, more bugs overall. And that's a shame because there's a lot of things about dealing with the zip format that are completely non-trivial. It is an old, crafty format with a lot of edge cases. Even though there is an ISO standard for the zip format and most of it is described in the freely available pkware app note, there's still a lot of surprises to be found when looking at zip files in the wild, like I did when I worked at itch.io. The zip format predates the universal adoption of UTF-8. Do not tell me that Windows still uses UTF-16. I'm trying to ignore that fact right now. And also they have a UTF-8 code page right now, so The zip format predates UTF-8, and that means the encoding of file names in zip files used to be whatever code page your system happened to be set to. Only in the year 2007 was the app note updated to document extra field values that indicates that the file names and file comments are actually encoded with UTF-8. This was probably fine when you passed zip files on floppy disks from one office to the next in the same country, but at itch.io we had a situation where a Japanese game developer used the built-in Windows zip creation tool from Explorer and had file names encoded as Shift-JIS, a successor of JIS X0201, a single byte Japanese industrial standard text encoding developed in 1969. The year we went to the moon. Most zip tools, however, treated that file as if it was encoded with code page 437, the character set of the original 1981 IBM personal computer, you know, the thing that gave the initials to PC, like PC and Mac, which, to be fair, is a pretty good guess in the West if the UTF-8 bit flag isn't set. Because the format only tells us whether a file name is UTF-8 or not UTF-8, the solution I came up with so that the itch.io desktop app could install games from all over the world is to take all textual content from the zip file, so you have file names and comments, and do statistical analysis trying to figure out what the character set is based on the frequency of certain byte sequences like these for Shift-JIS. This gives us a list of probabilities, and then you just take the highest and hope that you guessed right. I'm not aware of any other tool that bothers doing that. I think if I had to do it again, I would just require a standard archive format instead of trying to extract whatever stuff developers would shove in the file upload dialog of itch.io. That's not the only crafty part of the zip file format. For example, it doesn't really make a difference between files and directories. Directories simply have length 0 and their paths end with a /. What about Windows? Well, first off, I don't know if you knew, all Windows APIs support using // as a path separator. And secondly, this is one of the things the app note is very clear on. I'm going to quote here. The path stored must not contain a drive or device letter or a leading slash. All slashes must be // as opposed to backward slashes for compatibility with Amiga and Unix file systems, etc. Just to give you an idea of like when the zip file format was designed. Amiga was on their mind. Of course, if the zip was actually created on Unix, then the entry would have a mode, and in the mode bits you could tell whether it's a directory, a regular file, or a symbolic link. In the wild, I've noticed symbolic links tend to have their target as the contents of the entry, but of course that's not what the app note says. The app note says in the Unix extra field, there's a variable size data field that can be used to store the target of a symbolic link or a hard link, emphasis on can be used. Because there were so many different tools that could create zip archives, and standardization only came later with the ISO standard, which mandates UTF-8 file names, by the way, the app note takes a descriptive rather than a prescriptive approach. It simply documents the various zip format implementations found in the wild without making value judgments about the choices made by different software authors, which makes it a terrible standard. So if you want to support most zip files out there, you have to be able to read DOS-style timestamps and Unix-style timestamps, which are completely different. DOS timestamps, for example, are completely bonkers. They fit in 32 bits. Half for the time, half for the date. So far, so good. The day is a 5-bit integer, the month is a 4-bit integer, the year is a 7-bit integer, counting from 1980, mind you, and as for the time, is stored in hours, minutes, and 2-second intervals. I think of it every time someone says that IEEE 754 is weird because doing 0.1 plus 0.2 shows a lot of decimals after 0.3 or whatever. But okay, fine. Those are details you can probably ignore for files that have been created with recent or sane tools. I don't like using that word. But even the most basic fundamental aspects of the zip file format are slightly cursed. Like, most file formats start with a magic number, and then a header, including metadata, and then the actual body, the actual meat of the file. So pixel data for an image, or vertex coordinates for a model, things like that. But not zip. The only correct way of reading a zip file is to start from the end of the file and walk back until you find the signature of the end of central directory record. That's a mouthful, get used to it. And that's why, if you take a look at the zipcrate API, it requires the input to implement both read and seek, because even just to list the entries of the zip file, you need to be able to move around it. Doing this properly is not as simple as it may sound. Originally, the zipcrate made 4-byte reads starting from almost the end of the file, and then moved left by 1 byte every time it didn't match the signature of the end of central directory record, which was hugely wasteful. The async zipcrate, which was written later, improved on that by making reads of 2 kibibytes and moving to the left 2 kibibytes minus the size of the signature to handle the case where the signature would overlap 2 buffers, which is pretty smart. The comments mention a 500 times speed up compared to the zip method. The zipcrate eventually caught up in May of 2024 by doing 512-byte reads, which temporarily made it much faster until August of 2024, when they fixed a bug in the end of central directory record finding logic. A pretty fun one, actually. Let's dig into it. Most file formats, reasonable file formats, have some sort of framing mechanism. You read the file moving forward, and then you have records prefixed by their length. MP4, or rather MPEG-4 part 14, calls those boxes. Media authoring software tends to write a lot of metadata that media players don't necessarily know about, but anyone can skip over those boxes even if they were a completely unknown type. This property also makes it impossible to mistake data from the actual structure of the file. Each box has a type, and the type can be a valid UTF-8 byte sequence. There's never any ambiguity as to whether you're reading the type of a box or whether you're reading the name of the author of the media file, for example. However, in the zip format, because you're scanning from the end of the file going backwards, it is possible to read part of a comment or file path and have it accidentally match the signature bytes for the end of central directory record. And that's the bug that was fixed in the zipcrate in August of 2024. Instead of stopping at the first thing that looked like an EOCD signature, they now keep scanning the entire file all the way back and keep track of all the offsets at which signature-like things were found.
And if you like finding bugs, you love getting paid for it. Once in a blue moon, the interest of a giant corporation aligned with the public. Today is that move. Google Security has launched a patch rewards program to incentivize proactive improvements to security in open source with 3 main axes. 1. Harden existing C and C++ code bases, separate privileges, sandbox stuff, harden your memory allocator, and adopt patterns like the safe buffers programming model. 2. Build the scaffolding required to integrate memory-safe components into existing C and C++ projects. If Firefox, Chromium, and Android have done it, you can do it. 3. Take existing Rust crates with unsafe code and either reduce the amount of unsafe code or encapsulate it into self-contained safe abstractions. I am extremely excited about this program because it's not about doing the bare minimum to patch a specific vulnerability. It's about raising the bar for memory safety in critical pieces of software all at once and getting you paid to do it. Reward amounts range from $100 to $45,000. There's a 3 contribution limit per month. Patches must have been merged for at least a month with no reverts, and you can't submit anything more than a year old. Memory Memory safety improvements have a 2x reward multiplier until the end of 2025, 3x if it's done to one of the Tier 1 projects scoped as core infrastructure data parsers, which include a bunch of image, audio, and video decoders, along with FFmpeg itself. Will someone please harden FFmpeg? Other categories of Tier 1 project include Nginx, OpenSSH, liburing, and libzip. Head over to g.co/prp to read the complete rules and submit your first patch. Thanks again to Google Security for sponsoring this video and security for everyone.
But of course, reading an entire multi-gigabyte file by increments of half a kilobyte, seeking backwards every time, is pretty much the worst possible read pattern that you can do on any kind of device. Any buffering done in userland or in the kernel is woefully unprepared for that. And I was going to give you the example of a 4 gigabyte file that would require 8 million syscalls just to find the EOCD, but then I stumbled upon this comment in the GitHub repository.
I tried this PR on a 200 gigabyte zip file, 233,899 files within, that I access over a networked share.
And it's not like this person is doing anything wrong, technically, but maybe morally. By the way, if you're confused about all the complexity, like what's the big whoop in finding this thing, remember that you can have garbage at the beginning of a zip file or at the end of the zip file, or both, and most tools will still be able to decompress it just okay. Self-extracting zip files actually start with a native executable, and the zip file is just tacked on at the end, for example. In December of 2024, as I was rewriting this piece, a PR landed after 11 weeks of back and forth that rewrites the EOCD detection algorithm again, fixing the huge performance progression introduced in August. Is the async zip crate impacted by any of the bugs that were fixed and then refixed in the zip crate? Probably. It was last released in April of 2024, so who knows? I didn't check because I have my own zip crate, RC-Zip, which I believe to be the best of the three, not just because it also does character set detection like I explained before, but because contrary to the zip crate or the async zip crate, it is not tied to any particular style of I/O. Also, it has a very cool logo by the exceedingly talented Misha. There is ample precedent for Sen's I/O approaches, and I'm very happy to credit Geoffroy Coupry of Num fame for encouraging me to take that approach 5 years ago when I started working on RC-Zip. There's examples of Sen's I/O in the Rust ecosystem already. The Rust LS crate comes pretty close, although it still somehow ties itself to the standard read and write trait. The consumer of the library is free to choose when to call read TLS and write TLS, which means it integrates seamlessly with a completion-based library like MIO. The Sen's I/O pattern is even more common in the C ecosystem because, well, they have no standard I/O interface. You could have your APIs accept a file descriptor, but that would be fairly limiting.
No templates or fancy pitfalls like Java and C++. Programming C.
If we look at the Z standard decompression API, for example, it looks like this. You get a handle, you get an output buffer, an input buffer. Those buffers are simply pointer, size, and position. And when you call decompress stream, it updates the pause field of the input buffer and the output buffer. And then based on that, you can determine what happened. If the input's position is less than its size, that means that only part of the input was used during the call, and the rest should be passed again to the next call. This can happen if the decoder didn't have enough space in the output buffer, for example. If the output's position is less than the output's size, it means that the decoder is completely done and has flushed all remaining buffers. On the other hand, if the output's position is equal to the output buffer size, that means you should call it again with more output buffer. All these states are surprisingly tricky to get right. The decompressor might need more input, and you may have no more input to give it. That could easily result in an infinite loop. Instead, you should have a way to signal that you have no more input to feed it, and that it should error out if it thinks the input is truncated. Well, RC-Zip, my crate, does the same thing, except things are a little bit more complicated because, remember, the first thing we have to do is to scan backwards from the end of the file, and after that, we want to be able to extract individual entries from the zip file in any order, skipping over some, going back. It's pretty far from just a linear scan. To achieve this, it exposes two state machines. Archive FSM is used to read the central directory, returning an archive, and from there you can build entry FSM to read individual entries, knowing their offset, compression method, etc. Driving the archive FSM to completion involves following a simple loop. First we call wants read. If the machine wants more data, it returns some with the offset of where in the file it wants us to read. Most of the time that follows the last read we did, but not always. If it did return some, we call space, which borrows its internal buffer mutably. Rust doesn't deal with raw pointers, so we get a slice back, which means we know the maximum amount of data we can put in there. Once once we've performed a read, we call fill, indicating how many bytes we've read. As with the standard read trait, a read of size 0 indicates end of file. Finally, once we've fed our machine, we can call the process method, and I'm fairly happy with the design here because it consumes the state machine. You can see it doesn't take %self or %mute self, it takes ownership of self. If it's done, then it returns the done variant of FSM result, and we can never accidentally call any other method on the state machine again because it's gone. But if it's not done, if it wants more input and we should go around for another turn of the loop, then it returns the continue variant, yielding back ownership of itself to the consumer. Now we could of course go deeper into type safety with type states, but I'm fairly happy with the current design, which plugs fairly easily into both synchronous I/O via rczip sync and asynchronous I/O via rczip Tokyo. Well, I say that, but the rczip Tokyo implementation is actually fairly messy because asynchronous file I/O on Linux is a mess. You want to know how Tokyo does an asynchronous file read on Linux? It does it with a background thread. If you go look at the sources, you're gonna see spawn blocking. I think of that every time someone blogs about how reading a file with Tokyo is slower than with the standard library. Like, no shit, look at all the work it's doing. Also, this is just for files, by the way. It's not for TCP sockets, which is, how Tokyo is actually supposed to be used. Just reading 1 GB from dev urandom with Tokyo and with libstd, a terrible test program, we can see a difference in performance. The sync operation is consistently faster on a Linux server of mine. The actual numbers matter very little. What's interesting is digging in with lurk, an strace-like tool written in Rust. Also, did you know the strace logo is an ostrich? Now you do. His name is Strauss. With lurk, we can observe that the async version is doing a lot of this. It's making 128 kilobytes reads from one thread and then wakes up another thread, which queues some more work, and so on and so forth, doing that dance 8,000 times over the course of the program. By comparison, the synchronous version simply does this. One single majestic 1 GB read syscall. But it's not Tokyo's fault, not really. There simply was no good way to do async file reads on Linux until io-uring came around. If we change that, again, terrible test program to force it to do reads of at most 128 kilobytes, which is what Tokyo does anyway, and we add a Tokyo-uring variant, we see that it is consistently competitive with the sync version and consistently faster than the classic Tokyo by about 10%. I'm not giving exact numbers because I'm frankly ashamed of my setup, and you could tune the numbers to make it say what you want. What I do want to show you is the read loop of the Tokyo-uring version in terms of syscall. In steady state, it calls io-uring enter to submit the read operation, then epoll waits to wait for some operations to be completed, and write to wake itself up, because that's how Tokyo channels and wakers actually work. Here's part of a stack trace. You can see Tokyo-uring going into Tokyo, going into MIO, going into write. When submitting ops, that's how asynchronous syscalls are called in io-uring parlance, Tokyo-uring keeps a waker around, as we can see in their lifecycle enum. That waker really is just a boxed trait object in disguise. It has a data pointer and a virtual table. We've seen that recently. NLDB has limited support for Rust, but we can still print the local foo and see kind of what's in there. And we see 2 pointers, one to pointer, that's the data, and one to vtable. That vtable contains clone, wake by reference, and drop functions. And what Tokyo actually does when you call wake by ref is up to the MIO crate, which on Linux uses eventfd, an API that allows applications to create file descriptors just for the purpose of signaling events, which is cheaper than using a pipe, and it can be multiplexed via epoll, just like any other file descriptors like regular files or network sockets, etc. This kind of overhead of mixing like epoll and io-uring is why some folks chose to make their own runtime entirely separate from Tokyo. The Datadog folks made Glomio, the ByteDance folks made monoio, Vertex Clique made Nuclei. There's no shortage of interesting work going on. Adding a monoio variant to our test program, which is pretty simple, shows that the hot loop becomes just io-uring enter. It is, however, very important to note that this isn't actually a benchmark. Actual benchmarks barely indicate anything about the performance of real-world systems, but this test program didn't even attempt to indicate anything. We were just poking at various systems to see how they worked. All that said, I think monoio looks promising, so to cap it all off, I think we should make an rczip monoio package just because we can. We'll keep it simple and try to implement a single async function taking a reference to a file and returning an archive or an error. The file type here is from monoio, and so it comes with a native read@, method, but it has a signature that departs from the usual Tokyo stuff. That function takes ownership of the buffer and returns it even if the operation failed. That is a requirement for a memory-safe io-uring interface in Rust. Tokyo-uring does the same thing. It prevents the buffer from being freed before the operation completes or is cancelled. It's like we're giving ownership of the buffer to the kernel. There was an excellent P99Conf talk about that recently by me and my cat, Sherlock.
So if the sleep completes first and we throw away the read feature, then as far as the type system is concerned, we're good to mutate the buffer again or free it, but the kernel also thinks it's fine to write to this buffer whenever the read finally completes. And so we've got to use after free here. Our code is no longer safe, which means we've messed up the type modeling of our program.
That API makes the structure of our code a little peculiar. First off, our buffer is not a vec U8. We don't need to track capacity and length separately, and we don't need it to grow. So we simply have a boxed slice of U8 instead, of 256 kilobytes, fully initialized. Maybe unit is out of scope for today. After finding out the size of the file, we create the state machine and enter the loop. In the loop, if the machine wants a read, then the first thing we do is calculate how big of a read we can make. We don't want to read more than what the machine has room for, but also we can't use the machine's own buffer due to the current RC-zip APIs. It only lends us its buffer mutably. It doesn't give us ownership of it, so we can't transfer ownership of it to the kernel. We will need to read it into our own buffer and then copy it into the machine's buffer. So the maximum read size is the minimum between the size of our buffer and the size of the machine's buffer. Once we've established that, we can obtain a slicemut box U8, a type provided by monoio. It's like a slice, but it's owned, and it'll make sure that we don't read too much data. And as promised, we get the buffer back no matter if the operation was successful or not. So first we propagate errors, and then we copy to the machine's buffer however many bytes we've read, letting it know how much that was with its fill method. And finally, we can take back ownership of our buffer, which is stashed inside the slicemut we got back from read at, so we need to call into inner to unwrap it. And this explains why buff is a mutable binding in the first place. We were able to move out of it during a loop iteration on the condition that we put it back before the loop loops. If we didn't, the Rust compiler would gently but firmly refuse to proceed. And here's a program that uses it. Again, if you're a patron, you have access to that on the side. You can go and mess with it. The program runs on macOS with the legacy monoio driver, and it runs on Linux with the io-uring driver, which is what we're really interested in. We can see that from the io-uring setup call to the printing of the file listings, there is not a single read or write syscall. It's all happening as uring ops. The only syscalls we do see are brk, mmap, mremap, munmap, which are all related to heap allocation. We talk about heap allocation in the 14th part of the series, making our own executable packer, which you can check out on my blog. It is available for free for everyone right now. The implementation of the other state machine entry FSM is left as an exercise to the reader. It's simpler in a way because the reads are linear, and also more complicated in another way because it actually streams data out as the file is decompressed. But you only need to implement it once, and then you get support for all the compression methods supported by RC-zip, including deflate, bzip2, lzma, and zstandard. Although there are other avenues being explored to avoid that sync and async chasm like keyword generics, I believe the way forward is to simply implement formats and protocols in a sans IO way. I think that unifying libstd and Tokyo is the wrong approach because neither interface is compatible with modern IO APIs like io-uring. You know, making an API uring friendly involves rethinking a lot of things actually. And it's fun to see that other ecosystems that don't have any standard IO abstraction like C, or ecosystems with a much higher level of abstraction like Node.js, have been faster at adopting io-uring than something like Rust, where a lot of code was written against a different, less flexible model. See, I can say bad things about Rust. I'm not a shill. Probably.
She packed my bags last night, pre-flight. 0 hour, 9 a.m. And I'm gonna be high as a kite by then. I miss the earth so much, I miss my wife. It's lonely out in space on such a time.